Hi, I'm Sean Howard with VMware's Network and Security Business Unit. I'm going to talk today about just sort of an intro to the technical parts of NSX. We're going to go through and, in depth, maybe stretching it. It's only going to be about 25-30 minutes, but we'll give you an idea for technical audiences, kind of what the main components are and what the objective of different things are. So, as a level set, for those that may not be familiar, the basic premise of NSX is to abstract network constructs. It's not really to do anything mystical that you aren't familiar with already. You've got, so let's say here on the slide you can see that I've got a physical network of some type. There's some switches, there's some routers. Doesn't really matter for our purposes here. I've got a bunch of hypervisors connected to that. I've got these distributed virtual switches here. And presumably you've already got something like this, right? So you're already doing network virtualization to a certain degree. You've got these virtual switches. What NSX proposes to do is create this layer, so sort of, inserts some additional code into the switches. It creates this, it sort of federates them together into this, this virtual fabric, or you can think of it like a network hypervisor or something like that, but it's a layer of abstraction on top of the physical environment that allows you to build logical network stuff. So let's say in my virtual environment, I've got these little applications, right? The VMs you can see here represent different applications. And what I'm doing is creating logical environments on top of that. So I'm saying, all right, this workload down here has a couple of layer 2 segments, analogous to VLANs. It's got a load balancer. It's got some security policies on those VMs. It's got a router, different subnets. Same deal over here. This application works slightly differently, so maybe it has different rules, different firewall policies, different subnets, or maybe it has the same subnets as the other one. And then this application at the top here, you can see we're doing some bridging out to a physical thing. So we're saying we have this physical workload that for whatever reason has to be layer 2 adjacent to these VMs. So for each application, we're creating the logical topology on top of the physical topology without really caring how the physical topology works underneath. So if you're familiar with like Amazon AWS or Azure or our own vCloud Air, when you go out to create those things, when you go and say you get a little control panel that says, hey, I want to create a subnet, I want to create the equivalent of a VLAN, I want to create a broadcast domain and assign this subnet to it, and then I want another one. I'm going to hang these VMs off this one and those VMs off that one and route and have these firewall rules between them. And you're just defining this logical topology, and you don't really care in the end how the cloud provider goes about making that happen. If you go to EC2, for instance, or vCloud Air or any of these, and you say create a VPC or create a VXLAN or whatever, they're not really making a VLAN. They're not really reaching into the physical network and programming switches and telling them to create VLANs and stuff like that. It's just doing it logically on top of this. So all the big cloud players do something like this. They abstract the physical away, and then it makes it a lot more flexible. It opens up all kinds of possibilities to do this thing in an automated fashion, to do self-service, delegation, all that stuff. So that's the objective here. So how does this all kind of work? How do we make this happen? Well, there's a few fundamental things we have to do first. So NSX is a thing that you install into your environment. It's pretty simple to deploy in and of itself. It's like most VMware things. You download an OVA and you deploy this management console, and there's several layers to it. So the management plane, this NSX manager here, that's the OVA that you deploy. That's the thing that hooks into vCenter. It's the thing that gives you an extra tab in the vCenter web client that allows you to create logical switch, create logical router, that kind of thing. Then you have the control plane, these controllers. Now, the controllers don't fixate too much on them in terms of day-to-day management of the NSX environment. Most of what you'll be doing is through the web client. The controllers provide a bunch of behind-the-scenes coordination of things that we'll get into. You can almost think of them as the same thing as Active Directory domain controllers or something. They're replicating with each other, and you can connect to any of them. And you don't really have to think too hard about which. I mean, there are roles and things that different ones do, but you don't have to think too hard about it. You just connect to Active Directory and do queries, right? So, and then at the data plane layer, The data plane means this is the thing that's actually passing packets. That resides in the hosts. It doesn't reside in any particular place. It resides on every host that's prepared for NSX. So the benefit of that is all this other stuff can go down, and as long as one host in the environment is running, some amount of network stuff is passing through, right? So these things are independent of each other to a large degree. Now, this top thing here where they're saying self-service portal, you don't have to have this, but to realize the maximum value of NSX, you want some kind of system in front of it. NSX is meant to be consumed via API, even though there's a GUI with the web client and all that. In larger environments, what you're really after is the ability to just issue API commands from some sort of portal. Of course, our own vCloud or vRealize automation does this, even vCloud Director. There's a number of, OpenStack can do it. You can write your own thing. A number of customers out there, I see that all the time. People write their own Ruby portal or PHP portal or whatever. But the idea is you can consume it all in an automated fashion via a common REST API into the NSX manager. Again, cloud consumption layer, not necessarily required, but highly recommended to realize the most value. So deploying it, there's some stuff you do one time. And like I said, you download this OVA, you deploy the NSX manager. Once that's hooked in, you get this network and security tab, you go in there and say, okay, deploy the controller clusters. You basically just give them IPs, and then it automatically pushes the controllers out and sets them up and everything according to the parameters you fed it. You only deploy 3 controllers, that's it. And then you do this host preparation thing, and that's done on a per cluster basis. So like if I have 5 clusters in my environment and I want to run NSX functions on 4 of them, I would only prepare those 4 clusters. I wouldn't necessarily prepare the other one because you have to license an entire cluster at a time. So that's the licensing boundary too. I say prepare this cluster, it has 5 hosts or whatever in it. It then installs the VIBs and all that. It doesn't require reboots or anything, but it pushes all this stuff down and prepares them, and either for VXLAN, for distributed firewall, for whatever functions you select, and then you have to have licenses for all the sockets and the hosts that got prepared. There's another step called logical network preparation, where this gets into, we have some options with regard to how we're going to do. So if you're familiar with ARP broadcasts in layer 2, there's a function that sort of needs to be done that's like that, of discovering where IP addresses and things live. So sort of proxying ARP over layer 3 is effectively what's going on there. And we have options. We can do this over multicast. We can do it with unicast with the controllers. We can do a hybrid mode. So there's some thinking that has to be done at this level to decide, how you're going to lay it out. And then now we're talking about the consumption part. Now the consumption part, once you've set all, you've set up your physical fabric, you've prepared the hosts, you've deployed the controllers and so forth, you stop messing with that stuff. And that's, from then on, all you're doing is just saying, hey, deploy these logical network constructs. And on top of the physical environment that you've set up, you can deploy these, spin them up, spin them down, automate, grow them, change them, whatever. It doesn't really matter. That's, one of the main benefits to that, to abstracting these things up into the virtual layer, is that you can mess with them, and you're only really hurting the thing that you're touching. So in other words, much like a VM, you could delegate control of a given logical switch, or a given, you can delegate a given logical edge services gateway, for example, and say, hey, this subtenant can mess with this, and they can break their own stuff, but they can't break the overall environment the way that it would be if you, say, delegated control of a core switch to somebody and said, hey, just be careful, don't break the other VLANs. Can't really do that, right? So talk a little bit about the switching. So how does that logical switching stuff work? So taking a step back, remember in that first slide how we had a physical environment and I said it didn't matter what the layer 2, layer 3 situation is? Well, that's what logical switching, VXLANs, overlays, all this stuff is about. It's about not caring how your physical topology is with respect to layer 2, layer 3, whether each host could be on a different subnet for all it cares. But we need it to be logically that 2 VMs attached to the same logical switch are layer 2 adjacent from their perspective. So how does that work? And this, when you have to care about the physical stuff, you have all kinds of things like spanning tree and broadcast domain sizes and things like that, and that you get into that you don't really have to worry about with this. So with the, again, you architect the physical environment once, you then start doing these overlays on top of it in just a quick, easy fashion. So here's a slide I threw together that hopefully illustrates this a little bit better. So let's say this is my typical, hierarchical architecture, right? I've got the edge where all my services live. I've got a core. I've got a distribution layer. I've got an access layer. Now let's focus on the lower three hosts there, vSphere host 1, 2, and 3. Let's say that's the cluster that I build. I build a 3-host cluster. It's in row 1, so it falls into distribution switch 1. And let's say that I'm terminating my VLANs at the distribution switch, which is totally normal. So these VLANs, the red and green VLANs, are only available in row 1. And I say, okay, I create red VMs on the red VLAN, green VMs on the green VLAN. I trunk those VLANs down from the distro down to each virtual switch in each host. And that's great. A year later, or whatever, I want to grow this cluster. I want to add 2 more hosts to this cluster and utilize that capacity. And say, well, what does that mean? That means now I have to have that green VLAN extended over to this new row where it doesn't live. So we have to go to, as virtual admins, we have to go to network engineering and say, hey, do this. So focusing on the red one, we have to say, hey, take the red one and extend it across the core, extend it, and I've just caused all kinds of problems for network engineering. They've carefully compartmentalized their spanning tree. There's lots of reasons they don't want every VLAN on every port everywhere, totally flat in a network of any appreciable size. That becomes problems because of spanning tree blast radius, because of there's lots of reasons, really good ones, that we're stepping all over the network engineer's architecture, and it takes time, it takes RFCs, it takes care on our part. We have to go make sure that all those, 2 VLANs is not a big deal, but what if we had like 50? And then we have to make sure that those VLAN tags are trunked right on every single port, touching every host. This is the sort of stuff you get into when your VM is tied to a physical thing in the network, a VLAN. And that, in turn, it has to live on that VLAN because it has to be on a certain subnet. It has to be layer 2 adjacent to other VMs. It has to be behind a certain firewall to get its security policy, all that. You wind up with this sort of half virtual setup. So what an overlay does, now we're talking about VXLAN in NSX. There's other ones you may read about like STT, which comes into play in some cases in NSX. There's NVGRE, there's even IPsec. There's a number of overlays in the world, and it's kind of academic, which one's slightly better than the other. They all do this thing I'm about to describe. So we make it so that the physical hosts, the actual physical networks that those hosts have trunked to them, we don't care. As long as the hosts can route to each other somehow. So let's say that, the 3 hosts in row 1 are on the purple VLAN and the 2 hosts in row 2 are on the blue VLAN. Doesn't matter. We don't, and that's it, that we just have to give them one IP, right? And then they all route to each other. And then artificially, we create this VXLAN overlay. So the red VMs on the red VXLAN, as far as they're concerned, they're just, for you VI admins out there, they're just attached to a port group. It's like anything else. It's like you have a port group that's backed by a VLAN. In this case, you have a port group backed by a VXLAN. So you just attach the VMs that need to be on that VXLAN, that need to be layer 2 adjacent on a certain subnet to that virtual port group, and then they can talk to each other. They're none the wiser as to what's going on here. So how does this work under the covers? Whoops. All right. So my VM, let's say it's doing an ARP broadcast or something. It's doing, or it wants to talk to another VM. It's going to, and that is on its same subnet. Let's say it's already done its ARP broadcast. It's already figured out that it needs to talk to this MAC address. So it's sending a layer 2 Ethernet frame to what it thinks is something that's right there on its same subnet, or right there on its broadcast domain. And it does that, sends the standard thing. The host has a thing called a VTEP, which is that IP address on the blue or purple VLAN. And it then says, oh, okay, so you're actually, and it might involve the controllers and stuff here to look up where the target VM lives or do some multicast or something, depending on how you have it set up. And it says, okay, I need to encapsulate that with a layer 3 packet, send it over to the target host, and then the target host VTEP decapsulates it and hands the layer 2 frame to the VM. So as far as VMs are concerned, everything's normal. And you don't really have to think too hard about this either. It just happens. So when we say physical workload integration, I do want to real quickly point out that it's 21st century. You can route. It's not a big deal. You know, when I got started in the industry in like 1993 or 4 or whenever it was, routing was a big deal latency-wise. Now it's really not. So I would say to most customers that say, hey, I have a VM, I need to talk to physical things. If you're okay with having a routing hop, which in the vast majority of cases is perfectly fine, just do that, just route, and you won't have to do this bridging thing I'm about to describe. However, if you do have a situation where I have these VMs, they're on a VXLAN, and they must be layer 2 adjacent, meaning the same broadcast domain as some physical stuff, then we can do a bridge. So we can do this in software. Like if you're doing a migration or something, we can do this in software. If you really are doing a ton of this and it needs to be up all the time and super fast and everything else, you might want to look at hardware VTEPs. That's where that stuff comes into play. When you start talking about hardware VTEPs, layer 2 bridging, it's actually a pretty small, pretty narrow use case for most people. A better example, when they say physical workloads here, maybe imagine instead of servers, what we have is physical load balancers that have to be layer 2 adjacent because of the way the load balancers are configured. That's a more common use case. The default gateway needs to be a physical thing for stuff on a VXLAN. In any event, like I said, it's a relatively uncommon situation. If you're okay with routing, you don't have to mess with it. A lot of people at this point ask, like, well, how do I know, how do I see and troubleshoot this stuff? I have this overlay and it's, the network people are confused and can't troubleshoot things. So there's a few things. First of all, your network team is probably using some kind of NetFlow, some kind of something like that. And we can push NetFlow. We can push every flow that every VM on, everywhere in the entire environment, we can push that data to whatever system they're using, PRTG or Cisco's thing or whatever. We can also do ER-span, RSpan, ER-span, meaning we can mirror a port. We can say, take this virtual port, mirror every single packet that goes to it over to something that is running Wireshark that can look at it. We have SNMP MIBs, all the normal stuff. We can also syslog. So we can push to Splunk, our own login site, anything that does syslog, an SIEM system. We can push every single flow that ever happens. And I don't mean every single packet, but what I mean is a summary of each flow. This thing talked to that thing on this port, this amount of data, that kind of deal. We can send that, and you can keep a record of every flow that ever happens between all your VMs in your environment. It's you actually end up with a lot more visibility in most cases. And then we have some built-in things where we have a thing called it's here, it says NSX Manager Connectivity Check, but it's also called a trace flow, where you can nominate 2 VMs and say trace the flow, and it'll show you the entire path of VTEPs and everything, all the encapsulation, decapsulation that's happening. So there's a lot of tools in the tool chest there to troubleshoot things. Now, VMs in a single logical switch, you can see here, I got the web one, the app one, they're distinct subnets. Well, oops. The physical view, as you can see here, if you notice, the 2 hosts on the left are on the 150.0/24, and then there's a host on the right that's on a different /24, 250. But the VMs don't care. Again, VMs, they're all logically layer 2 adjacent. Now, routing, we get into distributed routing. What we're talking about here is, it's not just about multi-tenancy, but this is a use case where it's very valuable. Multi-tenancy, in our case, meaning you are a service provider and you have like lots of different customers, each with their own little bucket of resources, but sharing the same physical resources, physical network, physical hosts, but they logically each have their own bucket, which is how it is in vCloud Air, for example. Or maybe you're a company that has developer environments. You have a dev, test, prod, UA, and they're kind of separate. Maybe they're overlapping IP schemes, but they need to be kept logically separate. There's lots of use cases for multi-tenancy apart from the service provider thing. In other words, there we go. So you end up in those environments with some scale issues. You end up, especially via mobility, becomes a big problem. Now the benefits, distributed routing and hypervisor. What we're talking about there is, again, I create a logical router. It doesn't live in it. It's not like a VM. A distributed logical router is not a VM that lives on some host somewhere that everything hairpins to. it lives everywhere and nowhere. So in other words, I'm creating this logical router. I'm giving it interfaces just like if it was a physical router, or you can think of it like a Linksys router at your house or something. You just go into the web client, say, create this distributed logical router, and it gives you some tabs, like, to assign the interfaces and stuff. And it's got an uplink, it's got the two downlinks. Logically, it all works the way you would expect. I've got those two segments it's on that are connected to the logical router. Now, this controller thing that it's showing here, this is just control plane traffic for the router to figure out what VMs live where and what routes it needs to host. And but it's not like everything's data traffic's going to the controller or anything like that. So let's say two VMs want to talk. Oops. The routing is done in the hypervisor. Again, it's not like if VM1 wants to talk to VM5, it doesn't need to actually like go somewhere to be routed and come back the way it is with VLANs. It can just be routed by whatever local host. So we're talking about route peering here. So if we're creating distributed logical routers for each tenant through a cloud portal, through some automated process, and we assign routable, let's say we're not doing NAT and we're assigning routable IPs, we need those things to be announced on our physical network. So we can do this via OSPF or BGP. So those DLRs at the bottom level there can peer up to what's called an edge services gateway. And that's where the edge services gateway is the thing that talks to the quote unquote, real world, real VLANs. And you can see that on the left there, DLR traffic, that's just going, east-west traffic, we call it, between the hosts. Or you have something going north-south, needs to leave the data center, it goes out through that ESG. Now, the ESGs, the edge security gateways, again, these are the things that are on and off ramp to the physical world. So in this case here, let's just say we have one ESG and a bunch of DLRs below it. The aggregate throughput that we could do north-south, not east-west. East-west is as much as the host can handle, but north-south would be 10 gigabits. And that sometimes isn't enough, right? So we may want to have a bunch of DLRs or a bunch of tenants going up through an ECMP topology where we can have up to 8 of these ESGs in kind of, you can think of them in an ECMP cluster, or however you want to think of it. But the idea is equal cost multipathing, load balancing with OSPF or BGP can do this and balance the traffic. You can get up to 80 gigs north-south. So that's kind of your, but again, north-south is traffic like leaving the data center. It's not, which tends to, it's rare. I've seen maybe 2 customers that actually need all 8. Normally 1 or 2 is absolutely plenty because again, most of your traffic's east-west. Distributed firewall. So everything I've talked about, forget all that. This has nothing to do with any of that. It ties in a sense, but it is a completely distinct function of NSX, and many customers deploy it in the absence of all that other overlay stuff and routing and everything else. So what I'm about to discuss with the distributed firewall, you don't need, you can do the VTEPs and distributed logical routers and ESGs and all that, but you don't need any of that to do it. You can deploy DFW right on the exact topology you have today. So the idea is most companies, you can think of it like the I don't even know what they call it, but the bonbon theory or whatever, where it's like the hard outside and the creamy inside. Most data centers are like that. They have really hard perimeter security with layer 7 inspection and anti-DDoS and all this stuff, but inside they have either no or very little. Maybe a better analogy is your front door is big steel, wooden, something hard to kick down, but the interior doors are real weak. So it's not that there's no security internally, but it's much lower. How would you fix that? Well, you could put a bunch of east-west firewalls in. The reason nobody does this is it's not only is it tend to be cost prohibitive, meaning like put a stateful firewall at the top of every rack, it's also really hard to manage. So it tends to be that we focus and fixate on north-south traffic, but once something gets in, somehow or another, the weakest thing lets something in, now it can go crazy inside your data center. So distributed firewalling, it's basically putting every VM has a virtual NIC on a virtual port facing, on a virtual switch. And what the DFW does is it's a kernel module that goes into that virtual switch and firewalls the traffic before it can enter that virtual port. And it does this in a totally distributed manner at line rate. If your host, like the bus and NICs and everything on it, can push 20 gigs, this can push 19.9, or I mean, it's a very, very small penalty to pay in terms of bandwidth. It's effectively line rate, and the latency it adds is like 12 microseconds, not even milliseconds. It's really, really small, imperceptible. So now it's totally feasible to do this firewalling everywhere, on every VM, everywhere, all these traffic, and manage it centrally. So again, firewall rules enforced at the VNIC level. How you construct these firewall rules it's not the classic 5-tuple IP thing that a physical firewall has to do. It is 5-tuple in the sense that you have to say source, destination, what's talking, whether it's allowed or blocked, that kind of thing. But we can define the source and dest on things other than IP, things vCenter knows about. So it could just be VM names, whatever IPs those VMs happen to have. We're not enforcing it based, we're deciding based on their logical identity. So an example here would be I have 2 VMs on the web tier VLAN, let's say, and I want them to be able to talk to the load balancer, and I want them to be able to talk port 80 or 443 or whatever out to the internet, but I don't want them talking to each other, because I don't want it to be that if somebody does a buffer overflow on one of my web servers that they can then move laterally with a poison ARP attack or something, which is really easy to do. I can say, okay, they can talk out HTTPS, and then they can't talk anything else. And then I'm saying now they can talk 8443, maybe this is a reverse proxy down to a Tomcat server on the app tier or something like that, and then block everything else. And it doesn't matter, again, what their IPs are and whether they're on the same subnet or different subnets or any of that. It's enforced logically based on their membership in these security groups. So we can identify membership in security groups by lots of different things. It can be things like like objects that are in data, like the data center object in vCenter, or the virtual network, or the virtual machine name, or we could do it by IPs too. We can also do it with this thing called security tags, or other attributes in Virtual Center. Like I can just arbitrarily assign a bunch of tags to things that say this thing belongs to production, this VM belongs to finance, this one belongs to HR, whatever, and base security groups, and they can overlap. It's kind of like Venn diagrams. We can have things with multiple memberships and different things, and they inherit this cumulative security policy. It winds up being way fewer rules to manage than classic 5-tuple IP based, and it's much easier to troubleshoot and understand when you're looking at it. And the policy just, if you change the IP in a VM, if I'm basing it off the name, that's fine. If I'm basing it off security tag, fine. Change the IP. That's not how we're just, you don't then have to go into some firewall somewhere and update the rule or delete it. There's no security rule to clean up. So we can automate things like we can integrate with a number of different third-party systems to do things. If you're familiar with the old vShield endpoint stuff, where we're scanning scanning for antivirus at hypervisor layer, we can tie that in such that if a vulnerability is found on, say, a web server by this vulnerability scanner that we have tied in, it can then tell NSX, hey, add a tag that quarantines this thing until we're done remediating it. And during the time that it's quarantined, until you remediate it, it can only talk to the AV server, for example. We can automate that kind of thing. It's very dynamic possibilities. And finally, we're going to talk about the load balancing. NSX Load Balancer, it handles, I would say, 95% of use cases that most customers use an F5 or a NetScaler or something like that for. Now, I'm not saying you need to throw out your NetScalers and F5s and stuff. This is more for it's more commonly used, in my experience, for east-west load balancing within data centers. Big, high-capacity, internet-facing load balancers that you've already invested millions perhaps in, those stay in place, and when you start doing load balancing between, say, the web, app, and SQL tiers of an application, in that case, you can use a fairly simple logical load balancer that does all, again, 95% of things that you would ever want. And that you can deploy as many of these as you want, right? So I deploy these things, I give them IPs, I create VIPs and server pools and all this stuff, again, through the web client or through API commands, and it can do all this, normal sorts of things. There's site-to-site VPN services, there's SSL VPN services. This is typically done for migrations or to, in some cases, stretch layer 2 for an active-active data center type situation. And now we're going to talk about the NSX. So there's lots of different reference designs, technical papers, things you can look up that will talk about this. But the general idea here is the architecture, you can do whatever you want, right? We're not saying you have to do this architecture. But what we're saying is, let's say you were doing a layer 3 leaf spine or something where we don't have any VLANs extended past top of rack. The ones on the left, the compute clusters, can be on that, connected to that. It's only the edge clusters you can see at the right that we really have to care about real VLANs that get trunked to those hosts. So that's why we kind of concentrate north-south traffic to these specific edge clusters. That way we don't have to extend actual VLANs all over the place. And north-south traffic tends to be, again, much less than east-west. And then we would say, hey, you have your management clusters, which you should already have. Your infrastructure or management clusters is a separate thing in separate racks. Then, you don't want a circular dependency. But you don't have to do any of this. Small deployment of, I've seen NSX deployments that are 3 hosts. They just have everything consolidated into those 3 hosts. So again, we, in the virtual world, logically, faithfully reproduce layer 2 through layer 7 services. We can scale stuff out, central API to control this thing, central standardized thing. And there's resiliency. We didn't have time to get into as much as I would have liked to with regard to resiliency. But let's say you have a virtual edge services gateway. If you just check a box and say, make it resilient, and it creates a VRP pair and all that stuff. The resiliency story is the same as with physical routers and so forth. And this is also a platform for third-party services. We didn't get much into that, but think about the power of distributed firewall and how it has a tap basically on every single virtual NIC everywhere. And think about, we can allow access to that tap to any third-party provider that wants to do it. So there's a lot of IDS possibilities and things like that. So where I see a lot of customers going with this is the first project is don't change anything, don't install any overlays or anything like that. First project is inter-data center microsegmentation, meaning you're using the distributed firewall to implement a segmentation mandate without having to create a bunch of new VLANs and re-IP your stuff. It's a hugely valuable thing that people tend to do right off the bat. Then as they work towards actually automating their IT and moving towards sort of the next gen SDDC data center architecture, they start introducing the other elements. Again, you can ask questions of our panel here. You can register. There's lots of online free courses. There's hands-on labs I'd encourage you to do. And we also check with your VMware SC or account rep. We have public free 1 and 2 day class event type things that you can just go to. You just have to know that they're probably in your city if you're in the US. So thanks, and that is it.